sorry, forgot to do that. So humans are pretty amazing doing deformable object manipulation. And just for some like historical context on like what we're doing before we get to robots, this is a movie from the 1930s. It's like only 20 minutes long. It's on YouTube for free. Highly recommend checking it out. It's by this guy named Will Rogers, the guy that's on the horse. He was like a political commentator. He's like Jon Stewart of his time, of the 1930s. He was like beloved. But it was weird because he would do political commentary while doing rope tricking. But you know, he was just really good at this. And they even had like slow-mo back in the 1930s, which is kind of crazy. But this is like relatively incredible, highly skillful motions that this guy is able to do. And in this movie, one of the tricks that he does is right here. It's called a flying knot, and specifically a flying overhand knot. And there's a bunch of different types of flying knots, and this one specifically, you do a kind of upward twisting motion, and then you strike the rope at about like approximately the third, and that makes the bottom fly into that loop, and you create this loop shape. Let me show you a live demo of me doing this. So you have some rope, some weight at the end, and then you, so you can form a loop like that. We'll do a little bit better for you guys. So you can do that. And this is called a flying overhand knot. This is right here. If anybody would like to try it, you know, feel free. Even we can do it later as well. But just to get a sense of this task, it's right here. Awesome. Okay, so this is a task, right? And Chris gave me this task like, I don't know, like a year ago. And he was like, he did the task, and I was like, oh, wow, that's pretty cool. And I was like, okay, I think I could do that, right? I watched Chris do it, and I was like, it doesn't seem that hard. I can just, you know, move my arm, right? This is like a year and a half ago. And I tried it for like maybe 50 trials, and I was like, dang, this is a lot harder than I thought. And I kept on trying to do the rope trick, and I was like, okay, I'm gonna finally like say that I can't just figure this out. Let me watch a YouTube tutorial explaining how to do this. And in this YouTube tutorial, the guy shows you how to do the trick, and he shows it in slow-mo a couple times. But two of the most important things that he mentions in that YouTube video are you really need to pay attention to this contact point. Like when you're doing this loop and you hit it with the rope, that shape that you make is like the most important part of the task. And another thing he mentions is if you put weight at the end of the rope, it really helps you perform the skill better. Some of you might recognize this as the Intel RealSense tripod that comes in the box, but I just grabbed whatever that's heavy. And armed with this new knowledge, I was like, let's do this. So I started practicing some more, and eventually, within like, I don't know, like 15 minutes of practice, I was able to get my first ever flying knot. This is, this video cuts off, but I'm like smiling and excited right after that. This is cool and all, but let's get a robot to do this. Right? That's what you're here for optimal control of robots, not of humans, right? And now that I'm able to do this, I can give a demonstration, right? So I can give an example of how this skill should work to the robot. And the way that we capture this demonstration is the rope has these retro-reflective tape markers all along it, relatively coarse, like every 10 centimeters. And the handle has retro-reflective markers on it as well. And then we can track this with motion capture cameras and just measure the 3D position. So state estimation, assume that we have a really high accurate measurement of this task and are able to use that to feed it into our system. So let's see if I can do this. But I'm pretty sure I can do this task without looking at anything. Like I can blindfold myself. There? Yeah. So, you know, that kind of implies that I'm not really doing any closed loop feedback, right? I'm just executing some feed forward motion, right? There's no like reactiveness to this policy, right? It's just that I've optimized that command to succeed at the task. So naively, could we just get the robot to just copy the demonstration by just tracking the hand motion exactly, right? You'd assume that if I go in the exact same motion with my hand, then I would succeed at the task, because that's the only actuation mechanism here, right? Any questions so far? Does it kind of make sense? What I'm doing? Okay, awesome. So that's what we did. We took that human demonstration, the hand trajectory, and then tried to generate a robot trajectory that would try to track that hand motion as close as we can. And we take that trajectory that the robot does. If you have any questions about how this actually happens, I can explain later, but just imagine that there's some way to like generate that trajectory. We take that trajectory and then just run it on the real robot, right? Anytime you see this like black background with the green robot here, that's the real robot, just for reference. It's not a simulation. Unfortunately, it still fails, right? And you might be asking, why, right? Like you track that trajectory as close as you can. Unfortunately, we aren't able to track it exactly, right? The robot has different joint velocity limits and dynamics limits than the human, right? Like I can accelerate my arm much faster than this robot can. And also, the robot has a different morphology, right? One, it's like base is pointed upwards, does a different number of degrees of freedom, it has different workspace. So the kind of like transferability from the human domain to the robot domain, there's a mismatch there. And that's kind of what results in failure. It might be possible to track it precisely, but in this case, it doesn't. So let's do some learning, right? I, as a human, required practice in order to succeed this task, so presumably the robot also needs some practice. And in my mind, learning implies that we need to do some type of iterative improvement of our motion, right? So let's say we do an execution, there's some error in that command, and if we have some way to map whatever errors we get to a correction, then you would hope that eventually, by iteratively improving that command, you would reduce the task errors enough that you would succeed, right? And task error, I just mean like something that corresponds to whether you succeed or fail the task. I'll explain in more detail what that means. Does this kind of make sense? High level? Okay. So I'll go into a little bit more detail now. This kind of iterative process is very similar to an algorithm called iterative learning control. It goes by a bunch of different names like feedback error learning, or sorry, feedback command learning, error-based command learning, a bunch of different names. But iterative learning control has been used in a lot of different domains outside of robotics, and in robotics, it's specifically used in a couple different important domains, such as manufacturing, where you might have a robot arm that's like moving from point A to point B very quickly. And maybe the dynamics model is highly accurate, but you don't get like the optimal dynamics model. Like maybe there's like some like small mismatch in like the cogging towards, maybe like over time as it's running, the motors heat up, right? And you're not able to model that. But ILC helps these systems achieve even optimal performance because they do the repetitive motion. And since they do the same motion over and over again, if we can reduce the error each time we do that motion, then we're going to get like a very high performant command. And you kind of see an example of this with this quadrator, right? The quadrator starts right here and is trying to track that line, and each iteration, it gets closer and closer to tracking that line. And you kind of notice that each time it takes a relatively large step in making a correction, right? In just 4 trials, it can improve pretty significantly from this first iteration to the last iteration, right? So in general, ILC is this type of iterative approach, and I'll kind of describe how this algorithm works in a little bit more detail. So ILC starts out with this initial command, right? And this is like that feed forward time index command. It's not like a policy, right? It's just like some feed forward trajectory. Then you take that command and you apply it through the real system, and you measure what happened, right? You measure the state of the system, right? So with the quadrator case, right, you take a command, maybe like fly in a diagonal, then you measure what actually happened, and you take that like position and orientation trajectory that the quadrator actually took, and you compare it to your reference, right? Like if you're trying to move in a straight line, there's some error there, and that task error, you map through what's called an inverse model. And this inverse model, I'll explain more in detail, but this is like the core of ILC. It's some way to map these errors into corrections. And then you just effectively just take this correction and add it to your current command, and then you repeat. And then if you iteratively do this over and over again, you hope to converge to the optimal command for this exact setup, right? It's not like you're trying to optimize a bunch of different objective functions. It's just a single objective function from the single initial condition, and you're optimizing on the real system. Any questions? This is kind of high level, makes sense? I'll go into more detail about the inverse model soon, but yeah, where are you next? Okay, this is the next thing. Did I miss anything? Okay. Make sense? High level, ILC, this is kind of what we're doing. Can somebody explain the difference between like policy and command? Maybe? Like, what are we doing? What are we actually learning here?
For policy, you see state, and then based on that state, you have an action.
Yeah.
For open loop, you just roll out.
Exactly. It's like time dependent versus like state dependent, right? And there's some benefits to each version. So what actually is this inverse model, right? I mean, it has the word like model in there, so presumably there's a model involved. So if we have some model that's able to map the commands that we apply to some expected state of the task, right? And imagine for right now that this is like an oracle model, and it's like a perfect prediction of your real system, right? So it can perfectly estimate some command, the effect of some command to produce a task state, right? So like, imagine it's like a robot dynamics model. That's like an example, right? Like, imagine you had a quadrator model and it was like perfect, right? And you feed in some command and it outputs some trajectory, and that's exactly what the real system does. And if we assume this is like a locally linear model, then any like change in this command can be mapped to a change in that task state, right? And you kind of like squint and like hand wave, you can flip these things. And if you define some type of inverse model that can map some changes in that task state to changes in the command, you can now do this type of like error mapping, because this change in task state is actually just like a task error, right? And we can kind of hopefully take any error in the task and map it to a command update. Does that make sense? Our main goal is just find these command updates to hopefully converge and minimize that task error. That makes sense? Okay. In the linear case, this type of inverse model is actually the optimal learning operator. Like, there's no better version of doing learning than using an inverse model in the linear case. Unfortunately, our problem is highly nonlinear, right? The rope is bendy, everything is rotation-y. There's no linearness. But we can like linearize stuff and improve things, but I'll kind of explain why ILC is still really beneficial. Even though our problem is highly nonlinear and our model is unknown, right? I said in that previous example, if you have the oracle model and you just invert it, then you have that optimal command update. But since we don't have the optimal, we don't have an exact model of the system, right? Like the rope dynamics are very expensive to model, like the contact physics, the like bending physics, like FEA models for a rope are like possible, but very computationally expensive. How can we still use ILC, right? And this is the real strength of ILC, that you don't need an exact model of your system. You can just use an approximate model. And even with that approximate imperfect model, as long as there's some gradient direction pointing you in the right direction, then as long as there's some gradient direction aligned with the optimal command direction, by iteratively taking steps, you'll always converge towards the optimal point, right? If that kind of makes sense? A little bit? No? Maybe? So you kind of think of like, let's say I'm trying to push some block from here to over there, right? And the optimal direction is just go in a straight line. But my imperfect model is telling me to go this way, right? I can push it this way a little bit, right? And then from here, I can ask for another command direction. Maybe it says push it like that way, so I push it that way. But as I'm iteratively doing this, I'm making my way towards the optimal point, right? And I eventually succeed at the task, even with that imperfect model, with that imperfect system, because the gradients are correct, or sufficiently accurate enough. There's some gradient direction that helps. Okay, cool. And it's almost like we're doing trajectory optimization, but on the real system directly. So in normal trajectory optimization, you do optimization over a model, right? But here we're doing trajectory optimization on the real system, but we use gradient information from our model. And I'll kind of explain what the benefits of that are later. So in my setup, the initial guess, that initial command for ILC comes from the demonstration, and we run the real trials on the robot arm with the rope. This is actually Chris's PhD thesis, doing this like linear version back in the 80s. This is his book. It was actually a pretty interesting read. You should check it out. But you can kind of see here, right, like this top row are the commands that they're applying to the robot. And before learning, when they apply the command, there's some errors. And then after learning, there's some command update, those squiggles that are changed and the errors now are pretty much 0. So that's kind of what this is. So let's do some learning, right? I just kind of explained the learning algorithm. How would this actually run on the real robot? So what was our goal? Our goal was to tie the flying knot. Unfortunately, we can't just set the objective function as flying knot succeed or failure, because that's a really hard objective to learn, but we have a demonstration, right? So let's try to copy that demonstration. And before I was just copying the hand motion, but now let's try to copy the actual rope motion and learn to fit the rope motion. So if our rope does something different, we want to iteratively make the rope do the same thing as a demonstration. Make sense? Okay, cool. And this is what happens. So before learning, the red rope and the green rope are fairly mismatched, right? The green rope is the actual real rollout of the trial, and then the red rope is the demonstration. After learning, they're much closer together, but it still fails to tie the flying knot, right? You can kind of see the comparison here. So learning did actually improve something, right? It made the tracking much closer. But unfortunately, it's not close enough, right? The kind of demonstration gets cut off right at that contact point because we can't estimate the rope after contact because of tracking errors. There's some other reasons for that, but I will just say, let's say we're only trying to copy the demonstration up to that contact point. Kind of makes sense? Okay. So this fails. But if we call back to how I learned this task, right? I didn't learn it by just watching Chris. I watched a YouTube video. In the YouTube video, the guy said this rope shape at the contact is the most important part. And that kind of implies that maybe we should really pay attention a little bit more to this point as opposed to all the other points, because this is described as an important point of the task. And I'll kind of call this a critical point. And there might be multiple critical points in a task. A critical point is effectively just any part of the task that has a lot of significance or high leverage on the task success. And it can be any kind of time-based point relative to something that we can measure. So let's say a collision point, the start of the trajectory, the end of the trajectory, peak velocities. Any of these could be some critical point, anything we can measure consistently. And it can be both spatial or temporal. But in this case, it's just temporal. So if we're saying that this part is this part of the task is really high leverage, has huge impacts on the task success, why don't we just ignore everything else and just minimize errors at this point? And that's what we do. So this is what learning looks like over trials by just minimizing error at that critical point. And it succeeds. It was kind of fast. So, so right here is the critical point, and it's really low error, and then it eventually, if you do the follow-through motion from there, it succeeds. So that's kind of hard to parse, but here's a kind of spread out view. After learning, this is what the rope and robot look like for these time slices for both the critical point objective and the equally weighted objective. Does it make sense what the critical point objective is and what the equally weighted objective is? Maybe. Yes. Cool.
It made it a fifth trial, but how consistent is it to actually make it after that point of learning?
It depends on a couple different things. For that one rope, for a demonstration on this rope, and then the robot running on this same rope, it's pretty much within 5 trials maximum.
But then every time, even without more training, it makes it every time?
Oh yeah, I'll show you that in a bit.
Oh.
Yeah. Yeah, that's a good question. But here, can you see kind of the difference in what the critical point objective and the equally weighted objective does, right? At each time slice, the critical point, the equally weighted objective is pretty much copying the demonstration as close as possible, right? But unfortunately, at this most important part of the task, it's not low enough error to actually succeed, right? Whereas the critical point objective actually sacrifices performance at this whole beginning part to minimize performance right at that most important part of the task, right? And that's allowing you to achieve the high enough performance to actually tie the flying knot. Does that make sense? So in addition to paying attention to the right part of the task, you're also ignoring insignificant parts of the task to achieve higher performance at that part. That's kind of the really important part. Does that make sense? Cool. So I mentioned that inverse model thing earlier. And I said it was some mapping, but I'm going to walk through a little bit of the math of like what actually is that mapping and where does it come from. So first, let me just explain what the model is, right? And we actually use a really simple model of both the robot and the rope. The model of the robot is actually a kinematic model. So there's no robot dynamics going on. It's just whatever command we send to the robot, we expect the robot is going to track it exactly, right? So if we say robot is going to go from here through these points, right, then we imagine that the robot's going to exactly follow that point. And then the fingertip point that the robot takes is attached to a very simple model of the rope. This is like a very crude point-based model. So you have effectively just a sequence of point masses that are each connected by stiffness and damping constraints. So if it's bending, there's a stiffness force that's applied to try to make it straight. So it's kind of like a rope that like has some stiffness. And there's actually only 11 point masses. So it's a really crude, coarse approximation of the rope. But it's sufficient because the key thing is that we just need the gradient information. And specifically, and additionally, we don't model contact dynamics. Since the critical point happens at contact, we actually don't need to care about anything afterwards, right? I said we don't need to care anything about afterwards or before, right? But since we end the model right at contact, we don't even need to model anything afterwards, so we don't need to model contact here. So this model, right, maps some command through that kinematic robot model, through the like really coarse rope model to produce some task state. And this is kind of like a prediction of how good we are at matching that critical point objective. And here's an explanation of kind of like where that inverse model mapping comes from. So before I talk about the rope model, inverse model, let me just explain this in a linear case, very simple linear spring mass damper. So let's say I have a spring mass damper, mass that moves back and forth, and it's with linear dynamics. Those dynamics can be written down as some like state times an A matrix with the stiffness mass in there, damping in there, to get a new state, and some B matrix to convert whatever command you're applying to the force on the spring and the mass. So if we take, that's like one step of the dynamics evolution, right? And if we kind of sequence a bunch of those steps in a row, we can actually stack that whole thing into one linear equation. So it doesn't super matter following this precisely, but effectively in the linear case, right, I have some Z matrix of all my future states, that's like the task state. This middle matrix, that's like my dynamics matrix, and that maps my initial state and then my commands to get that task. Does that kind of make high-level sense, maybe? Yes? Yes? Sort of. Okay, I mean, the most important thing here is that it's just like some linear mapping between a command and the task, right? And since it's linear, the delta command can be mapped to the delta task state, right? Like if you're over here and you do some mapping, that's the exact same thing as being at 0 and doing some mapping. That's all that means. And since it's linear, right, you would hope that you can just take the matrix and invert it, right? And then now you can map those task states to the command updates. But unfortunately, that matrix is probably not square, probably not invertible. So we can just use a pseudo inverse, right? And if you've ever taken a math, I don't know, some math class, I don't know when you would learn this, but the pseudo inverse is actually the same thing as solving a linear least squares optimization problem, right? The pseudo inverse effectively is just like a mathematical simplification. It's a solution to what this linear least squares optimization problem would produce. And since this is written down as an optimization problem with the dynamics constraint right here and an objective that tries to minimize our like matching error, this optimization problem, which is a quadratic program, can be arbitrary, right? Like I can change those optimization values to whatever I want, right? As long as it's quadratic, so I can solve it as a QP, it was simple, but it could be nonlinear, right? You could do whatever you want. Have people heard of like a quadratic program before? QP? Maybe? Yes, yes, yes. No? Yes, maybe? Okay. Effectively, it's just an optimization problem with quadratic costs and linear constraints. there's like more details, but there's like different classes and stuff, but yeah. And in our case, right, we want to optimize that critical point objective. So we could just stick that in the optimization problem, right? We're minimizing the error at that critical point, and then we stick our system dynamics model, that like rope and robot model, that we linearize about some trajectory, just so it's a linear constraint. And I mentioned those like joint velocity limits that we're violating, that we can't violate in order to like actually make the robot move. We can also just stick those in this optimization problem. So the ILC is aware of like, don't violate the robot dynamics, but try to generate this optimal trajectory. And over trials, the green rope and the red rope are able to optimize towards that critical point, right? So on the 5th trial, it's able to succeed, and each trial, we iteratively reduce the errors. Does this kind of make sense, what we're doing? Sounds good. Maybe? Okay. So I showed you the ILC running with a demonstration on this rope, right? Sorry. Demonstration on this rope, and then the robot also learns on this same rope. But what would happen if I gave a demonstration on this rope, and then I asked the robot to learn on different ropes, right? So we've got a variety of ropes here. This is a stiffer rope. This is a much thicker rope. This is like a metal chain that's like way heavier. This is like latex tubing, so stretchier. So just to provide some variety on like what the ropes, whether the robot could learn on that specific rope. And this is what learning looks like. This is what the learned successful command looks like on every rope type. And it works on pretty much every rope I've tested it on. So that's like a shoelace. It's a very thin rope. This is like a very thick rope. This is a metal chain. The video is silent, but it's actually like super loud. It's kind of scary to do the metal chain. It's like, but the robot's able to do it. And the kind of combinations of ropes and masses I selected were just combinations that I as a human could do. I think it would be interesting to see if it could do combinations that I as a human couldn't do, right? I think that like you could get super good performance. And this is kind of what the learning curves look like. So the critical point objective is minimized on like a log scale over iterations, and it succeeds at some points. But unfortunately, you can see that sometimes the learning cost goes up. And I'll talk a little bit more about why this happens a little bit later. But that's one of the future works that we want to explore.
So are they all learning from that one initial demonstration, or are you doing additional demonstrations?
No, just one demonstration.
And are they all the same length? And like
Yeah, so they're all the same length. That was like an assumption that we made. I think that you could like kind of like stretch the demonstration for different lengths. Or there's like other approaches. I'll talk about more later.
Did you maybe try, like, when it learned with one rope, immediately switching it without learning more, see what happened?
So that's exactly what we did. We took the learned command on rope A, and then applied that successful command on rope B, and then saw how many additional trials does it take to learn on another rope. And you can kind of see that for most of these rope combinations, it took more than one trial, which means that the rope dynamics were different enough that you actually needed to learn something. It didn't just transfer automatically. For some ropes, like rope 7, which is the latex tubing, every single command succeeds, which is, I guess, interesting because I don't know why, but latex tubing was just very robust to doing the flying knot. But that's something we discovered through doing this. And for some transfers, it actually fails, right? Rope 5 and rope 6 are like the really thick ropes, and maybe that has something to do with why this transfer failed. But effectively what happens is it's almost like we fit to one rope, and then we're unable to unfit and transfer to a different rope. Yeah. Does that make sense? Awesome. So in all these cases, I gave the same type of demonstration, right? I did the flying knot in this fast motion. It's going in the loop this way, but I can actually do the flying knot a couple different ways. So this is like a slower version. This is like a side swipe version. This is a inverse version. I swear the video is not just mirrored, it's actually inverse. And the robot's able to learn in all these cases. It's just 4 versions. There's actually more different versions of doing the flying knot. You might remember the Will Rogers version is like swinging start and then you do it. But I only did the versions that I could do so that I could actually demonstrate it to the robot. And then this is what you were asking earlier. After learning succeeds, it actually has a 100% success rate. So with the final command, you're able to just keep on running it. I ran it like 40 times. Could probably run it more, but I just got tired. And it had 0 failures. And I think this is more a note on the fact that this task is deterministic and less about us actually optimizing robustness. I think there's ways to do ILC in a robust optimization way, but this isn't doing that, right? We're just like using the fact that the task is repeatable and deterministic. So, yeah. And in all of these cases, I mentioned that rope model, and the rope model has the stiffness and damping parameters. I actually didn't fit those parameters to anything, right? I just picked the same parameters and I fixed it for all trials. So we don't even need to optimize the rope parameters per rope type. Does that make sense? So.
But you still tune them for different ropes, right?
No.
Like the chain, you use the same parameters.
Same parameters. It's literally the exact same like parameters, exact same code, just running on the rope, the chain. So it's like really fitting to the real system, and that gradient information is what's super useful to telling us what direction to go in. There's obviously some amount of like regularization that I do to make it like be like nice and work, but like those are parameters that I just fixed. I didn't like change them. So you might be asking, okay, fine, you can tie a flying knot, cool and all, but does this actually work on other tasks? And that's what I'm working on right now. So this is like a cleat lasso task. The rope is configured a little bit differently, right? The end of the rope is like fixed to a specific part, and there's actually multiple phases of this task. So I'm trying to learn each phase separately. So this is like phase 1 of the task. So I gave a demonstration in that motion, and then the robot is able to do that first phase. It obviously is not as cool as the second phase, but it's able to at least succeed and show like proof of life on this task. And the second phase is like almost there, dealing with like engineering state estimation issues. But yeah.
Does it also work with the critical point?
Yeah, so this is using a temporal critical, like the same critical point, but in addition to a specific time, I use a specific part of the rope, right? So you might notice here, like most of the rope is just a long kind of straight thing, and that actually doesn't really matter that much. It's not very important. Only the part where the loop is, that's the most important part. So it's almost like a temporal and spatial critical point, and that's what I use in this task. Okay.
How is that any different from the critical point in the...
Before it's spatial, but it's like, I spatially do minimize everything, like the whole length of the rope.
Oh.
Like
Oh, I see.
like for the flying knot task, like pretty much the whole rope was important. Like you needed the bottom of the rope and the top of the rope to be in the right shape. Like when you're how to demonstrate this like loop, yeah. Pretty much this top loop part and this bottom part all matter at that contact point.
At a specific time as well. Right?
At a specific time. In this one, it's a specific time and a specific part of the rope. And I mean, right now I'm just defining these things as like specific instant moments, like specific frame in the trajectory. But like honestly, they should be probably a little bit more humpy and smooth, like maybe like a local neighborhood of like spaces and time. Yeah. So high level takeaways, and then maybe a quick discussion if you guys have thoughts or input for me as well. Yeah. So I would say attention is all you need. Obviously, this is a very loaded term, but I think that this task level attention is really critical to understanding what are the parts of the task that have the most leverage towards succeeding, right? As a human, when you're learning a new skill and a coach instructs you to do something, they are instructing you with critical point information of what parts of the task to pay attention to. And that really informs how humans are able to learn it efficiently. So I think that that is critical for robots as well. And minimizing errors at those critical points at significant moments are allow you to ignore the other parts of the task that are irrelevant, right? Or matter less towards the task success. And it allows you to achieve are more likely to succeed at the task overall. And ILC in general, I think enables really fast learning directly on the real system, right? You don't need to do huge amounts of data collection in simulation. You don't need to do large amounts of data collection from humans. You can just do direct learning on the real system. And tasks that are ILCable are ones where you have a repeatable goal, right? So if you're able to start at the same initial condition and then try to achieve the same goal over and over again, then you can ILC that task. And these dynamic, fast motions on these deformable objects kind of enable that repeatability. And finally, I think these critical points can come from instruction. Instructional material more broadly, like YouTube videos, books, diagrams, anything that kind of informs the intent of how you should learn. Or they could come from random search, right? If we have these like GPUs, these large parallelizable tools, we could do large amounts of simulation and try to autonomously find critical points and strategies for doing things. So those are kind of like the high-level takeaways. And I mentioned a couple limitations earlier, right? Learning can sometimes fail. And one kind of hypothesis for why learning can fail is these like unmodeled collisions, right? So like if the rope, as it's flying up, hits the robot arm before the critical point, then it's something that we didn't model. We don't have any gradient information telling us how to correct that, right? So learning diverges to some part of the state space that it doesn't know how to recover from. And in addition, that like critical point being that like loop shape at contact, that's not the actual goal we're trying to achieve. The actual goal we're trying to achieve is tie a flying knot, right? And this kind of loop shape is just a proxy for that goal, right? So it only has some relation to whether we're going to succeed at the goal. It doesn't tell us 100% are you going to succeed or fail. There's instances where like you can do that loop shape, the bottom flies into the loop, it falls down, it's almost about to get there, and then it flies out of the loop, right? And that means you failed the task. But that wasn't captured in the objective. Additionally, state estimation issues right now, I'm just trying to fix that. And these learning instabilities of where learning can diverge. In most of these examples, I use the same model, but I also did tests where I changed that model so much that the gradient information was in the wrong direction. And that made it so that learning can sometimes move the robot to a part of the motion kind of space where learning isn't able to recover. Like maybe it's just like throwing the rope in some random direction and it doesn't know how to recover from that. So maybe strategies of doing like line searches or other optimization techniques could help resolve some of this. Any questions? Yes?
So for the second demonstration, do you need to like stand at the same location of the robot?
The second demonstration?
Yeah.
Like for the different types of demonstration? Or?
Like you throw the rope on the.
Oh, that one. Yeah, that's a really good point. So in this exact setup right now, yes. You kind of, that's why this is on like the stool right here, because I'm trying to lift it up to the same height that I would be. And I think that ILC, in this case, should be able to resolve that. Like I shouldn't need to put in the exact same place, right? Because if my critical point is just like the shape of the rope relative to the cleat at some like location, I could rotate it, I could move it to the side, right? And the objective function is telling you to minimize that error, so it should be able to succeed. I don't have proof of that actually working yet, but the hope is that I'll be able to do that. But yeah, that's a really good point. A couple of discussion stuff, but let me first just go over some future work maybe. I'll just like this. So another kind of problem I wanted to work on from the same Will Rogers movie was called a pretzel knot, where you tie a pretzel into a rope. This is me doing this. I probably have like a 10% success rate doing this. It's very, very difficult. In slow-mo, you can kind of see why this test is a little bit more challenging. The rope is actually hanging off of my arm, so there's contact there, and the critical point's like right there when the bottom passes through that loop. I think so. Obviously, choosing specific critical points is kind of arbitrary right now, but I think it could be more so informed from like instructional material eventually. So this is like a slightly more challenging task, and I also think that like you don't need one critical point. You can have multiple critical points, right? And that's especially true for these multi-stage tasks. So maybe you learn different phases of the task with ILC separately, and then you learn how to combine them. And maybe even in one phase, there's multiple critical points in that specific part, just like other complex rope rope skills. I also think this framework's pretty much directly extendable to 2D deformable objects, like things like whipping a blanket or a towel out, doing this thing is called a Daplo star. You can do like some crazy spin moves to make that work. But it would really suck if I had to learn all of these tricks and skills in order to demonstrate it to the robot, in order for the robot to succeed. It would be much nicer if we could just learn directly from a YouTube tutorial. And I think the first step to getting there is really figuring out what are these like maybe more abstract critical points as opposed to like very metric information. So in this flying knot case, I really don't care whether this like point on the rope is like exactly 1 centimeter this way or this way. I more so just care, are you forming a loop and what's the size of that loop, right? And the concept of a loop is a lot more of an abstract concept that we can extract more directly from instructional material. And that's kind of what the guy says semantically in the transcript of like the YouTube videos. And if we can somehow be able to autonomously extract those critical points from instruction, we can, by leveraging like foundation models, VLMs, then we can have a system that autonomously learns complex skills from just watching instruction. Or the system could just be directly coached by a human. Right? Here are like 2 other problems that like I think could be achievable, but it would be very difficult for me to learn how to do these things. This one on the left is called a Texas skip, and the one on the left is like an Indiana Jones, like swinging across the vine. It'd be cool to try this with a humanoid, maybe. But yeah. Any questions? Or we can just talk about stuff. I think one. Oh, sorry. Oh yeah, I was just gonna ask, like, are there problems that you guys are working on right now that you think task-level ILC or something could be applied, or what might be the limitations to applying task-level ILC? Hopefully, you kind of understand how it works at a high level, but. And the like key limitations, right? We have to learn a command. There's to be repeatable goals. You should be able to reset it somehow. Yeah. No problems? Any problems?
So how robust is it to like slightly varying initial conditions? Like for example,
yeah.
Like if you're folding clothes and the stack slowly gets higher,
Mm-hmm.
or stuff like that.
Yeah, that's a really good question. I think that's definitely like one of the areas I'm trying to work on next is like, how can you do like near ILCable problems, right? Like it's repeatable, but it's like maybe it's slightly different every time. I think the example that I try to think about is like tennis, right? Like every time you get a forehand, if you're practicing that same shot, you can repeat that motion over and over again, but the exact position that the ball is going to be in is likely never the same, right? But hopefully ILC would still be able to learn that command, right? It's almost like you're trying to do this flying knot task, but every time you do a trial, you change the mass of the weight at the bottom, or some change in the system every time you do it. And you never get to like iteratively apply those commands to the same command, or apply those updates to the same command, but you still collect some useful information maybe to succeed at the task. So I think like some of the stuff that Chris talked about last time, like those memory-based methods, I think those could be really useful in building a policy from ILC, but it's an open question. That was my first question, actually, of like, can ILC learn a policy instead? Or like, how can we adapt the system to learn a policy? And I really think that like the strength of ILC is in these like local searches and local learnings. It's not really great in trying to discover like global strategies, right? But those global strategies could come from like instruction, demonstration, right? If you did a flying knot in this demonstration and you asked it to try to learn the inverse one, that's a much harder thing than just me giving a demonstration in the inverse one and then it just learns that, right? But there's a question of like, what type of like global search would fit really well with ILC, and how do you adapt these like memory-based or other types of methods to capture that policy effect? Make sense? Kind of. Yeah.
I guess another big part of the ILC is the model, right? So obviously you had to like come up with the model yourself. Is it possible for because I guess I would think that you don't actually need the information from the full model to succeed at the task. There must be some like local area that's most important.
That's a really good point. Yeah, I think that like there's another thing I missed to put up here was that like the model structures are also manually specified, right? Like I came up with this rope model structure, but if I'm trying to learn from like a YouTube video, that model structure might not be there, right? So I either need to build that model structure from demonstrations or somehow come up with some type of model that gives me that gradient information. And as you said, you only need that local gradient information as long as you stay in that local region, right? So there's I mean, yeah, that's a really good point of like, could we just build those models directly from data? Probably yes. Do those models need to be globally applicable? Probably not. So are there data efficient ways to do this? Yeah. Good question. Okay, last thing, or like thing I was gonna ask about is, do you guys have tasks that you do in your daily lives or that you know of that are dynamic or interesting that you think that could be ILCable? Or not ILCable, just any dynamic task? Obviously doesn't need to be useful, or don't even think about a robot trying to achieve it, but just some interesting task. Do you have any hobbies? Frisbee? Frisbee? Yeah. I think Frisbee is definitely like interesting. It's very, it's very repeated, right? And you have like an objective that you're trying to hit, right? And you're resettable, like you can just pick up a new Frisbee. So that'd be interesting. There's a question of like, when the wind starts blowing, how do you know how to adapt your command, right? As a human, I'm sure you as a Frisbee player, or are you a Frisbee? Okay, yeah, you as a Frisbee player are able to know how to do that. Is it just that you've seen different wind configurations before, so you know how those commands operate? Or do you have some internal model of how the wind impacts the Frisbee? But yeah, that's an interesting task. Any other tasks? They don't have to be robot related, obviously. Like shoveling snow. Very dynamic. Like constructing a house. Like making balloon animals. No ideas.
It's not really like useful one anyway, but
I don't care. Does it seem like I can?
like after you do your bed sheets, you kind of need to like like
yeah.
plan it out.
That's very useful. That's way more useful than most things. That's a. I think people have like, that's a task that people have like tried as well before, but I don't think there's like general ways to do that either. But yeah.
Maybe like flipping a pancake.
Yes. Flipping something. Yeah. That's an interesting example. Do people flip things in non-pancake contexts? Like non-cooking? Is there like
wok tossing?
rock tossing?
Walk. Like when you're
When you're like frying. Oh yeah. That's also a good example. It's almost like I'm trying to get at tasks that you almost can't do quasi-statically, right? Like you can fold a t-shirt quasi-statically, you could fold a t-shirt dynamically, but you couldn't do your bedsheet unfolding. It would be much more inefficient, much harder to do quasi-statically. You'd have to like pick up each strand and pull it tight, as opposed to like just doing this motion. Right? The flying knot task, you just like implicitly in the task it's dynamic. So. Yeah, I don't know. There's other tasks that you.
If you like pick up your phone from your pocket and it's the wrong way, it can be
like reorient, in-hand dynamic reorientation,
Yeah.
or like spinning type things.
Yeah.
I feel like pen spinning is always in that category too. Yeah. Is there other tasks? I feel like a lot of sports, honestly, are like like I know that somebody's working on golf, like golf is. ILCable, like I don't know, tennis is what I say, but yeah. Does anybody work on like deep learning stuff?
I actually have a question.
Oh, yeah.
Do you think that you could learn like a function that represents your inverse model at like arbitrary states instead of like cultivating it? But then I don't know, because like let's say you have some random trajectory that you want to follow, then you could update that trajectory with like the learned inverse model. Maybe I don't know.
Yeah, potentially. I think there's a question of like, how do you get the data? Maybe to learn that inverse model. Maybe it's the same question of you just need to do it locally, right? If you do it locally, you don't need that much data. You can use lower order function approximators, or you can use some priors or something. Yes, I think that you can learn the model, and you can learn the inverse model. I think it's just a question of like, how do you do it in a way that works still, right? And is providing those useful gradients. I think the nice thing about the analytical model is that like, it's interpretable.
Yeah.
But the deficiencies being that it is limited in its model structure and representation.
As well, like learning from like practice, because I assume after doing it that many times, you yourself have an internal sort of model of how the rope
Right.
kind of performs.
But the thing is that like, even though I maybe have an internal model, right? Like I don't think I can express that to you, right? Like maybe I can say like, oh, your loop is not high enough, so maybe you need to lift your arm higher. That's a very semantic model that I'm giving to you, right? It's like semantic, it's symbolic. It has, there's no numbers that are associated with that, right? So like somehow translating that information into something that's useful for the robot to know what to do. Maybe an LLM could be helpful there. But internally, like I can't even tell you what model I have, right? So I don't know what to give to the robot as its model.
Well, but do you think the robot can directly learn just from like looking at the robot?
Yeah. I think especially failures can be informative, right? So let's say I do the task, I succeed, and I do another attempt and it fails, right? And I have some local region of demonstrations of failures and successes, and I can even map those to like some metric amount of failures and successes, like as in like I'm like this far away versus this far away. Then I have some local model that can tell me which direction those gradients are in, right? Unfortunately, my demonstrations are in a different task space or in a different command space than the robot, right? I can't stick like an electrode in my brain to measure exactly what I'm doing, right? And also my arm is different motion, different morphology than the robot, right? So there's a domain mismatch there that I think it's possible to resolve, but it is non-trivial. Right? Okay, it's like 4:30. Do y'all feel like you understand task level ILC to some extent? Okay, cool. Do you have any questions on like any part of the system? Any non-research stuff as well? To answer any questions. Yeah.
Regarding the deep learning help,
Yeah.
I see ILC as a way to make it like efficiently and not have to throw compute at it. Wouldn't using deep learning like completely erase that efficiency?
So, I think I have a bias against deep learning because of its large parameter representations. But really, the strength is that it's able to represent those high parameter, high dimensional things in a way that is useful, right? Like, let's say I have the rope, or like, maybe here's an example in like the quadrotor space. In like the quadrotor racing space, like people did work on trying to get drones to fly through gates really, really fast. And at those speeds, the like fluid dynamics of the air have huge impacts on what you're supposed to do while you're flying, right? And they did like really extensive CFD modeling of the air, of the like wake of the air from the other drone, and they still aren't able to model that perfectly enough for it to optimize over that. So what they did was they had it run through the real course with the best model they have, and they used the data of what actually happened in those trials to learn a residual dynamics model that they put into their simulation and then did optimization over that. And that like little bit of like extra model fitting that they did from the real data, those like residual dynamics, are really easy to capture in a neural network compared to capture in an analytical model. Because of the representational capabilities of the neural network, right? It's really hard for me to write down exactly what is going on in something that I don't necessarily even understand, right? As opposed to having an arbitrary function approximator that can just capture that and then output what is going on.
And what at that point you use like a differentiable difference like reinforcement learning?
Yeah. Or like, are you saying like I guess like ILC can still be useful even if you have a learned dynamics model, right? And like, it's not like ILC needs everything to be low parameter in order to work. It being low parameter helps with the data efficiency. But if you have neural networks that can really help you figure out what parts of the task to care about, so if it gives you a really low dimensional representation, then your ILC problem is easier because you only need to search over that low dimensional representation. You don't need to search across like image space, right? You can just search across some latent space.
Yeah.
And if deep learning can do that compression for you, then like that's like one advantage that it could have. But yeah, there is a trade-off there of like larger parameter models always need more data. So there's a question of where does the data come from? And if it's an easy place that has lots of data, like the internet or something, then you're good to go. But make sense? Okay. Oh.
For all your like trials, you use mocap to get like this data from it. Like,
Yeah.
what happens if like that information is there's some uncertainty in that information? If you didn't use mocap.
Right. Yeah. That's a really good point. I think that like I've simplified the problem right by using mocap. I think that like you could just use like RGB cameras and try to do the same exact 3D state distribution of the rope. It's probably possible. But there's a kind of question of like, do you really need all that information, right? Like, do you really need to track the rope exactly, right? If all that matters is that you need to form a loop and you need the bottom to go through that loop, those abstract concepts are much easier to measure in like RGB video semantically, as opposed, or like directly measure those lower dimensional abstract representations, as opposed to trying to track the exact precise 3D or orientation and location of the rope, right? So as you make things more abstract and as you pay attention to the right parts of the task, you're also making every other part of the problem easier. You're making the modeling easier, you're making the state estimation easier, you're making this parameter space you have to search over smaller, right? But yeah, like I think that's like one part of it. I think that you're also saying like uncertainty measurement. Right now I'm not estimating uncertainty at all. I'm just assuming everything is perfectly modeled, or like perfectly estimated. But yeah, I think that's like, you could totally include uncertainty models of the state estimate, like noise models of the sensor, or also do uncertainty modeling of the models themselves. Like you can optimize over a class of models if you have uncertainty in that. But yeah, you could totally just stick like a noise model in that ILC optimization. So if you have like a sensor model that predicts some uncertainty, you could just put that in there and have it optimized over that uncertainty as well. And like people totally do that as well. Okay, that's good. Well, that's all I have. Hopefully, learn something maybe. If anybody has any questions or help with the project or anything, I can